Hey everyone, welcome to another session of CeerazzleDazzlePhysics. In today's session, we're going to be talking about how to add capacitors in series and parallel. So how to add capacitors in series and parallel. So we'll start with the following diagram here. Okay, so in the following diagram, guys, you'll be able to see that we have a cell on one side here connected to three capacitors in series. Right, let's start with the following. Let's talk about the charges on each one of them. So let's say on the power supply, yeah, or the cell, well, it's a cell, this one is positively charged, +1. What will happen is all the electrons along this part of the wire, yeah, that part of the wire, guys, that they will move onto it. So the electrons will move onto it, leaving the other one with a deficiency, and therefore it will become positive. And they will be of equal magnitude, guys. So look, it will be equal magnitude. It's not more positive at the bottom compared to the top. It's the same amount. What about the opposite side now? So the opposite side, it's negative. Let's draw that with so it's negative over here. So all the electrons on this terminal are going to be pushed away, repelled away, making this one negative. And it will be of equal magnitude. So the charge is the same on both of them. So it's not like -1 over there, -2 over there. It's -1, -1 over there. Right, so what about the charges of the ones in between? And what's going to happen to the ones in between? Well, just think about this part of the wire. Let's look at that part of the wire right now. Let's talk about the electrons within it, yeah? Right, so along this part of the wire, here, the electrons will sense that positive charge and they will therefore move towards it. So the electrons move towards it, therefore making this terminal negative. Right, what about this part of the wire now? So the electrons upon this part of the wire will sense that negative charge here and be repelled and they will be moving away. So this terminal becomes negative. Okay? And obviously, if that terminal becomes negative, the opposite terminal has a deficiency, it will be positive. There we go. And same thing over here, it will be now become positive. Wonderful. So clearly you can see that they have now all become charged. And look, the charge across the top one over here, the charge across there, yeah, is the same as the charge across there. They're not going to be different, guys. So the charge across one of them is the same across each one of them. So therefore we can say the following. We can say that the charge stored, let's say the charge in total, or yeah, so over here, charge total, that went in. So Q total, QT, will be equal to, let's call this one, the total charge stored here, Q1. This one will be Q2. This one will be Q3. So the charges across each one of them will be the same. So QT will be equal to Q1, which will be equal to Q2, which will be equal to Q3. Make sure you can see that with my explanation, yes? They all have the same charge upon each one. Right, what about the voltage now? So let's talk about the voltage. Let's talk about the voltage total, yeah? So the voltage total going in. So the voltage total going in, if we can remember Kirchoff's first law states that the sum of the voltage in equals to the sum of the voltage out in one loop. Therefore, the total voltage going in equals the total voltage coming out. So therefore, let's call this one the voltage V1, V2, and let's call this one V3. So therefore, we know that the voltage T will be equal to V1 plus V2 plus V3. Yes, the sum of the voltage in equals the sum of the voltage out. Wonderful. Right, each of these are capacitors, so each of them has a capacitance. So we have, this one will be, I'll have a capacitance of, let's call it C1, the other one will be C2, this one will be C3. They all have a capacitance value, C1, C2, and C3. There is a relationship between capacitance, charge, and voltage. We can remember that capacitance is equal to charge stored per unit volt. Happy with this? Charge stored per unit volt. Right, I'm going to now replace this equation at the top, this one over here, using that formula, this formula over there. So rearranging this formula, therefore we know that V is equal to Q divided by C. Okay, so the voltage across the terminal, we can replace that with QT divided by CT. We can replace it with QT divided by CT. And now I can replace V1 with Q1 over C1. So this will be equal to Q1 divided by C1 plus V2. V2 will be equal to Q2 over C2 plus it will be, V3 will be equal to Q3 divided by C3. Okay, happy with this? Right, you also know that all the charges are the same, so all of them are the same. So from this first statement at the top, look carefully, we know that QT, all of them are going to be the same over here. Okay, so let's replace all the Q's. So we know this one will be Q over CT is equal to Q over C1 plus Q over C2 plus Q over C3. Okay? Then we're going to factorize some of them out. So this one will become Q open bracket 1 over CT will be equal to Q open bracket 1 over C1 plus 1 over C2 plus 1 over C3. Happy with this? Then, obviously, mathematics, we can cancel them out. So Q cancels out with Q over here. Therefore, we end up with the following expression that 1 over CT, the capacitance in total, is equal to 1 over C1 plus 1 over C2 plus 1 over C3. Wonderful. So here we go. Right, okay, so we end up with the following expression. There we go. 1 over the capacitance in total is equal to 1 over C1 plus 1 over C2 plus 1 over C3. So obviously dependent on how many capacitors you have in series. And obviously you can use that formula if you want to combine them all to find the effective capacitance. Okay, so that's how you add the capacitors in series, guys. So when you add them in series, you can use the following formula. What about in parallel? So let's do the parallel one now. Right, so now we're going to do capacitors in parallel now. So how can we derive a formula to work out the capacitance in parallel? Right, so first of all, we'll do roughly the same thing. So let's talk about the voltage going in. Yeah, so let's call voltage total over here. There we go. And let's call this one V1. Let's call this one V2. Let's call this one V3. And obviously, there's still going to be the same value of the capacitance, guys. So this will still be capacitor 1, capacitor 2, and capacitor 3. Right, the next thing is going to be talking about the charge. Right, if I make this terminal positive now it's slightly different. If this terminal is positive, obviously it won't just make this terminal positive, but all three of them will become positive. But how much? How much though? So if I make it 3 over here, let's say charge of, I don't know, plus 3 over here, obviously each and every one of them must get a share of it. So this one will be 1 there, 1 there, and 1 there. And obviously it can't put 3 on each one of them because where's that extra charge come from? But have a look, guys. So if it's plus 3 on one side, it gets shared across each one of them. And same thing for the opposite side. Let's make it minus, minus, minus. 3 of them there. It gets shared across each one of them. 1, 2, 3. Over there. 1, 2, 3. Yeah. So the charge is being shared now. So let's just talk about the charge here. So let's say the charge going into this one over here. Let's say the charge going in. Let's call it the charge in total. That will be equal to, obviously, the addition of all the charges across all the capacitors. That'll be equal to the charge across the first capacitor, Q1, plus the charge across the second capacitor, Q2, plus the charge across the third capacitor, Q3. Adding all three of them, 1, 2, and 3. What about voltage now? What about the voltage? So the voltage total will be equal to, now Kirchoff's first law, the sum of the voltage in equal to the sum of the voltage out in one loop. They will all have the same voltages. So therefore, V total will be equal to V1, will be equal to V2, will be equal to V3. Happy with this? Okay, we still remember that capacitance is equal to Q divided by V. Now let's go back to the equation at the top. So I'm going to use this equation. Q total is equal to Q1 plus Q2 plus Q3. Right, so now I'm going to use the formula Q is equal to C times by V and plug that everywhere. So QT is going to be equal to CT VT, which will be equal to Q1 is now replaced by C1 V1, plus Q2 will be equal to C2 V2 plus C3 V3 over here. Everyone happy? Now from here, guys, we know that the voltages are the same. So therefore, we know that the voltages are the same. We can say the voltage is the same. So therefore, we can say CTV will be equal to C1V plus C2V plus C3V. Because all the voltages is the same. Look at that formula at the top. All the voltages are the same. Factorize it out. V times by CT is equal to V open bracket C1 plus C2 plus C3. Bang, over here. Then we can cancel out the V's on both sides. So therefore, guys, the capacitance in total when they're in parallel with each other, so when they're in parallel with each other, will be equal to the simple addition of them plus C3. Obviously, depending on how many you've got. Okay, so we have now worked out the formula for capacitors in parallel now. So for capacitors in parallel, you simply add them. Series, 1 over CT is equal to 1 over C1 plus 1 over C2 plus 1 over C3. But in parallel, you simply add them. Okay with that? And obviously, a lot of kids get confused between the resistor ones, because the resistor ones, when they're in series, you simply add them. But look, it's almost the reverse. Yeah, so don't get confused with the resistor ones here. Okay, so we've just done both the proofs of them. Obviously, you've got to be able to be familiar with Kirchoff's laws, charge laws, and C is equal to Q over V. But it's quite straightforward, guys. Make sure you can do it in your spare time. Right, and that's it for another session of CeerazzleDazzlePhysics. I know it was very mathematical today, but obviously you should be comfortable with using the previous formulas to get to this position here. That's it. Ciao, ciao, goodbye, and good luck.